Take a plain piece of square paper. Folding it horizontally, vertically, and diagonally marks a flat plane with a permanent network of sharp, straight creases. These physical folds represent the straight lines we study in geometry. When they sit on a flat surface like this, we can track exactly how they interact with one another. If we isolate just two of these lines, let's call them L and M, they cross to form an X. This intersection creates four distinct angle sectors around a single center point, which we'll label A, B, C, and D. Because a straight line cannot bend or curve, these two lines can only meet at one exact point. Once they cross, they continue moving away from each other in four straight directions. This physical constraint means that the four angles at the center are not random sizes. Because they share that same unbending intersection, their measurements are linked by a logic we can prove using simple arithmetic. Let's test this by assigning a value of 120 degrees to angle A. By knowing just this one measurement, we can use the geometry of the lines to determine the values of the three remaining angles. Look at angle A and angle B together. They both sit on the same horizontal line. Since any straight line represents an angle of 180 degrees, these two adjacent neighbors must add up to that same total. We call this a linear pair. Subtracting our known 120 degrees from the 180-degree total results in 60 degrees. Angle B is now solved. Now we follow the slanted line. Angles B and C also form a linear pair. If we subtract the 60 degrees of angle B from the 180-degree line, we find that angle C is 120 degrees. One more step. Following the horizontal line again, we see that angles C and D must also total 180. 180 minus 120 leaves us with 60 degrees for our final sector, angle D. We've completed the intersection. Notice the result. Angle A and angle C are both 120, while angle B and angle D are both 60. The angles sitting directly across from one another are identical. We need to know if this was a coincidence or a rule. If we remove the numbers and look at the relationship between the labels, the geometry tells a more permanent story. These pairs sitting across from each other are known as vertically opposite angles. We can prove they are always equal using algebra. We know angle A plus angle B is 180 degrees. We also know angle A plus angle D is 180 degrees. This means the two sums are equal to each other. Both sides of our equation include angle A. When we remove that shared value from both sides, we are left with a simple truth. Angle B must be equal to angle D. Because perfectly straight lines do not bend, they force vertically opposite angles to be equal in every single intersection. You can now solve for any missing angle in an intersection by using 180-degree linear pairs and identifying vertically opposite angles. Let's put this to use with a problem from your textbook. In this new diagram, two lines intersect, and we know only one thing. One of the angles is exactly 48 degrees. Using the rule we just proved, what is the measurement of the angle sitting directly across from that 48-degree sector? Then use the linear pair rule to calculate the measurements of the two remaining adjacent angles. So post your calculations in the comments. Once you see the geometry of the lines, these problems become simple exercises in logic. See you in episode 2.